In this video, we're going to be solving for a roller coaster problem at 3 different positions using circular motion concepts and calculations. So first of all, if you're approaching a circular motion problem, you're taking a look at the sum of the forces and setting that equal to the mass times the centripetal acceleration, which is mv squared over r. Now, when you're taking a look at the sum of the forces, anything that's going towards the center of the circle would be considered positive, and anything pointing away from the center of the circle would be considered negative. Now, when you take a look at these 3 different scenarios, only one of them you can clearly see the actual circle. For the rest of them, you sort of have to imagine the circular path that it's taking. So for our first position, your circle is right here, and there is the center of your circle. So we can focus on that certain spot to see if things are centripetal, pointing towards the center of your circle, meaning that they are a positive force, or if they're pointing away from the center of the circle in the radial outward position, and they're a negative force. For our second one, as you can see, the bottom of the curve is going downwards, so the circle would be going more upward in this direction, so the center of your circle is right over here. And then for your last case, the center of your circle is in the center of that loop right there. So let's go ahead and analyze each of these situations. So what you want to do first is go ahead and draw the forces acting on the person in each of those positions first. All right, so now that we've drawn the forces acting on the person in each of the 3 cases, which is basically just the normal force and the force of gravity, let's analyze one at a time. So at this position over here, where the person is at the top of a hill, you could see the center of our circular path is right there. Our FG is pointing inward towards the center of the circle. So that FG is going to be positive. And then the normal force is pointing in the radial outward position. So you're going to subtract that, and that's going to be a negative value that equals mv squared over r. Now what you can do is you can go ahead and plug in all of those values, and then we can go ahead and find the normal force, and that normal force is going to be the person's apparent weight at that particular position too. So let's go ahead and plug in our values and see what we get. So one value that wasn't written on the screen was the 60 kilogram mass. So went ahead and added that in. So our FG is mg, which is mass times 9.8 minus the normal force, and then m, our v squared, and our r given from the problem. Now, if you add Fn to both sides, it goes to the right side of the formula, and then you subtract this number over here, which is 214.29, from our FG of 588, and we get 373.71 newtons. So this person's apparent weight is less than their actual weight. Their actual weight that they normally feel is 588 newtons, and because they're going towards the top of a hill, they have some inertia heading upwards, so that releases some of the force that they push down into the seat. Therefore, their normal force is less, and they feel a little bit lighter. Now, the big difference between the first situation and the second one is now if you look at the center of your circle, your Fn is pointing inward towards the center of the circle, and your Fg is pointing away. So your Fn is your positive force, and your Fg is your negative force. So for this one, we know that our Fn is our unknown. Our Fg is still 60 times 9.8. We already know that's 588 newtons from our previous problem. And then if we plug in mv squared over r using the v and r provided, then we basically have everything we need. And then our Fn equals, and then we add 588 to this number over here, which is 420, and we get 1008 newtons. Okay, so this one is significantly larger than our first answer because now when you're going downhill, your body's pressing into the seat more. You get more of that equal and opposite force from the normal force. Therefore, you have an apparent weight that is greater than your regular FG of 588, and you feel as if you are 1008 newtons. Now, for our last scenario, now we have a roller coaster where you're upside down in the loop. And as you can see, both of these force vectors are pointing inwards towards the center of the circle. So they're both actually positive. So it's Fn plus Fg. Again, we know Fg is 588 equals mv squared over r. Our m is 60. Our v for this one is 7. And then our velocity, or excuse me, our radius is 5. Okay, turns out once you multiply these two and divide them, you actually get 588. So if you subtract 588 from both sides, your normal force comes out to 0 newtons. So at that particular moment, they feel weightless based on the velocity that they're moving and the radius of the circle. So when performing these circular motion type problems, what you want to do is make sure you sum up all your forces, make sure all the ones that are positive are the ones that are pointing towards the center of the circle, but of course you have to identify what your circle is. And we did that with our purple dashed line, our orange dashed line, and then just looking at the loop of this actual roller coaster. And then anything that's pointing away from the center of that circle, we make that a negative force. We set that equal to m times our centripetal acceleration of v squared over r, plug in your number values, and then you can go ahead and find your normal force, which is your apparent weight. Or depending on the situation, you can obviously plug in different values to solve for different unknowns. So I hope that was helpful to you in solving a roller coaster problem using circular motion concepts and calculations. Thank you for watching and listening.